So today, we are going to be covering nodal analysis. Nodal analysis is a very, very powerful circuit analysis tool. If you can apply it and its counterpart, mesh analysis, which we will learn on Monday, if you can apply them well, this class will get significantly easier for you. Okay? The caveat there is being able to apply it well and correctly, because if you're applying it incorrectly, everything goes out the window. All right. Sorry, not nodal mesh, nodal analysis. So what nodal analysis is an algorithm for determining unknown voltages in a circuit using multiple applications of KCL. All right. So I am going to lay the steps out in a very specific order. Truthfully, most of them don't have to be carried out in this specific order, but I'm trying to get your brain to think of this as a simple process, okay? So if you do these steps in the order that I am describing them to you correctly, you will get the right answer 100% of the time, okay? So I'm not saying you can't improvise or anything like that, but what I'm saying is if you're asking me a question about it, the first thing I'm going to do is, did you do my steps in my order? And if your answer is no, then we have to do a lot more work than if you said yes, okay? So let's take the following circuit. Let's say that we have a 10 amp source connected to an 8 ohm resistor connected to a 15 ohm resistor, like so. Let's call this guy a 20 ohm resistor. And this will be difficult enough. A 5 amp source, like so. All right. And let's say that we are interested in determining the voltage drop over the 15 ohm resistor, positive polarity on top, negative polarity on bottom. Okay. Is there any simplifications that we could make to this circuit to help us analyze it in any way, shape, or form with our current level of circuits knowledge? They're not in parallel, so none of the resistors are connected in series. None of the resistors are connected in parallel. This is using superposition, and it wouldn't be particularly difficult. But aside from superposition, where we're kind of breaking the whole circuit down and solving it twice, there's really no method that we could do to simplify this. Okay. So in performing nodal analysis, our first step will be to identify. That's not how you spell identify. Our nodes. So I'm going to do what I've been doing throughout this class and highlight our various nodes using different colors. And we can see that this circuit contains 4 nodes, okay? Hopefully nothing wild or crazy there. We've been doing this since practically day 1. Our second step will be to assign a reference node, okay? So let me talk about what this means. If I wanted to determine the amount of potential energy stored in this stylus thing, I would have to be careful to define a reference, right? So what I mean by that is the potential energy stored in this stylus, because I'm holding it up in the air, as gravitational potential energy, right, from our physics classes. So it has a certain amount of potential energy with respect to the surface of this table. It has a certain amount of potential energy with respect to the surface made by the floor. It has a certain amount of potential energy with respect to the center of the Earth's spherical or oblate spheroid selfness. I can't think of the right word, but you're getting what I'm saying, right? The reference is very important in determining the amount of potential energy that this thing has. Well, our reference choice in our circuit is going to be critical in determining the amount of electrical potential energy we see anywhere else in the circuit. Okay, so what we're going to do is we're going to pick one of these 4 nodes, and we are going to say that that node has a voltage of 0 volts. It will be our reference for everything else, and all other voltages will be measured with respect to that. Okay, so that is what I mean by assign a reference node. We pick one of those 4 nodes, and we say that that node has an exact finite potential of 0 volts. We can pick any node we want, but generally speaking, picking the node that has the most elements connected to it will make the problem the easiest to solve. So in this case, our top left node is connected to 2 elements. Our top right node is connected to 2 elements. Our top middle node is connected to 3 elements. And our bottom node is connected to 3 elements. So I personally would either choose the top middle node or the bottom node. Which one do you guys want to work with? Bottom, okay. So I am going to denote that I have chosen this one as my reference node by placing, connecting it to ground, right? So this ground symbol here means that the voltage at this node is equal to 0 volts. My third step will be to assign nodal voltage. Okay. So what that means really is that I'm just going to assign a voltage variable to all of my non-reference nodes. So I could call this node at the top left VA. I could call this node in the top middle VB. And I could call this node at the top right VC. And so I want to explain what these nodal voltages really mean, okay? The nodal voltage is a shorthand notation, right? We define voltage to be the difference in electric potential between 2 points in a circuit. A nodal voltage means that the voltage measured at this node with respect to ground is VA. This voltage VB means that between this point and ground, we have a voltage VB. And VC means that between this point and ground, we have a voltage VC. Okay, so all of those nodal voltages, effectively the polarity is already defined. The positive polarity terminal is attached to where we have the variable, and the negative polarity terminal of that voltage is ground, always. So with that in mind, what could we say about the nodal voltage VB and the voltage Vx that I've referenced in the circuit? They are the exact same quantity, right? Because they are both the potential difference between that green node in the middle and the pink node on bottom. So VB is exactly equal to Vx. It's just two different ways to look at the same voltage, right? One is as a nodal voltage because it's with respect to ground. That voltage Vx is the voltage drop over that resistor, but they represent the exact same quantity, okay? So this will be an aside here. So I'm going to do it in a different color. Let's say that I wanted to look at this voltage V20, the voltage drop over my 20 ohm resistor. If I want to put that in terms of my nodal voltages, what I do is I say that it's the nodal voltage associated with the positive polarity terminal. So that would be VB minus the nodal voltage associated with the negative polarity terminal, which would be VC. So I could say that V20, the voltage drop over my 20 ohm resistor, positive polarity on the left, is the same as VB minus VC. And so I hope it's coming pretty obvious that we can actually determine any and every voltage in a circuit if we can figure out what these nodal voltages are, because then we can just do simple combinations, Kirchhoff's voltage law and all that kind of good stuff, all right? So that's step one, step two, and step three. Step four will be to apply KCL to all non-reference nodes. All right. I'm going to erase this V20 thing here real quick because I just wanted to talk about that for a moment. So I'm going to write here, if my pen thing will work, KCL at node A. I'm going to use that third formulation of Kirchhoff's current law that we talked about, where all of the currents exiting a node sum together to be equal to 0, all right? The reason I am using that particular formulation here is because we will find that it's going to give our nodal voltage VA a positive sign in this equation. All instances of VA will have a positive sign, and all instances of other nodes will wind up with a negative sign. So it's making sure that effectively it's an easy way to map things out, all right? So the currents that are leaving node A is this guy directed down, and this guy directed to the right. Everybody okay with that? Okay, so these are the currents that I'm defining to be leaving node A. And so they're the ones that are going to show up in my equation. There are two currents, so I should expect there to be exactly two turns. So what is the current flowing down from node A towards our reference node? Negative 10 amps. Now for one, probably quite a bit harder, at least it'll seem hard at first. How am I going to express the current flowing to the right through the 8 ohm resistor in terms of my nodal voltages? So VA minus VB represents what, Ian? Not a current, because it's the difference in voltages. Okay, exactly correct. So what we should have, and I will explain this, would be VA minus VB divided by 8 ohms. Okay. VA minus VB represents the voltage drop over the 8 ohm resistor, positive polarity terminal on the left, negative polarity terminal on the right, so that my current in red is flowing into the positive polarity terminal. Okay, so that's the way that I'm going to establish my signs and my convention for doing these currents. All right. So effectively, what I'm saying, there is some voltage V8 across my 8 ohm resistor. The positive polarity terminal is associated with node A. The negative polarity terminal is associated with node B. So the voltage drop is VA minus VB, and the current is flowing into my positive polarity terminal. So Ohm's law tells me that the voltage drop divided by my resistance is equal to current, and all of my signs are what they need to be. Okay. Then I set this guy equal to 0 because my current, Kirchhoff's current law equation should only have 2 contributions because we were only adding 2 currents together. I would then apply KCL at node B. So I'll draw these currents. We're now going to have the current flowing to the left through the 8 ohm resistor, the current flowing down through the 15 ohm resistor, and the current flowing to the right. We're going to add these 3 terms together and set them equal to 0. So test it. How can I express my current flowing to the left through the 8 ohm resistor in terms of my nodal voltages? I don't know what you're talking about, positive or anything like that right now. The current flowing to the left through the 8 ohm resistor. VB minus VA over 8 ohms, exactly correct. Okay. So just because I have this plus V8 thing over here associated with my red currents, none of that means anything once I move along to node B. Okay. So I should see that node B is the positive polarity terminal for all of my terms when I'm applying Kirchhoff's current law at node B. So perfectly correct. VB minus VA over 8 ohms. All right, I'm going to pick on somebody else. Ms. Miguez. Did I pronounce it correctly? How can I express the current flowing down through the 15 ohm resistor in terms of my nodal voltages? So VB, Vx isn't a nodal voltage. So ostensibly it should not show up in my nodal voltage equations unless I can absolutely help it, okay? So we talked about this a minute ago, right? Our potential difference for our KCL equations when applying the nodal analysis method should be in terms of nodal voltages only, right? So the nodal voltage that the current is leaving from is VB, and the nodal voltage that the current is entering to is our ground terminal, or 0, right? 0 volts. So effectively, we're doing the exact same thing we did for the previous current, right? We had the node the current left from, which was VB, the node the current was going to, which was VA, divided by the resistor value, right? If we do the same thing to the current going down, we have VB minus 0 over the resistor value, or just VB over 15 ohms. Yes. VB minus VA plus VC. I'm not following. Yeah. Ian, are you raising your hand or are you processing information? Okay. So this is really going back to what I talked about at the very beginning of the class, where we said that VB and VX represented the exact same quantity, right? Because they're both the voltage drop over the 15 kilo ohm resistor, but that voltage VB is with respect to ground, whereas that voltage VX is with respect to the pink terminal, but they're the same thing, right? So any voltage, whenever we're taking the voltage drop over a resistor with respect to ground, we shouldn't have a second term or second voltage there because it's just going to be zero. So a little bit of practice will help this set it. Okay. Now let's talk about the current directed to the right. Mr. Aycock, I haven't picked on you for a while. What's the current directed to the right through the 20 ohm resistor? VB minus VC over 20 ohms. Perfectly correct. Set this equal to 0. And now we move to node C. All right. So for node C, we're going to take this current directed to the left through the 20 ohm resistor into account, and this current directed down through our 5 amp current source into account. So we should see that we have exactly 2 terms in our equation. So, Ms. McCarthy, what is the current directed to the left through the 20 ohm resistor? VC minus VB over 20 ohms. Absolutely correct. I like that as we continue through this example problem, people's authority in which they're giving the answers is increasing. That's what I'm hoping for. All right. John, what is the current directed down? Just 5 amps. So I now have 3 equations. Sorry, I need to set this equal to 0. And 3 unknowns. Now, you could go through the huge headache of rearranging these equations and finding least common denominators and all that kind of crap to make them look nice and neat and pretty. You guys have calculators for a reason. Your calculators can effectively do this for you. So what I am going to do here is I'm going to effectively show you how to look at this guy and figure out what's supposed to be going into your calculator. All right. So we're going to set this up to where we have some number multiplied by VA plus some number multiplied by VC plus some number, VA, VB, VC is equal to a constant. So what should the coefficient of variable VA be in our first equation? 1/8. What should the coefficient of VB be in our first equation? Negative 1/8. And then the coefficient for VC, 0. And our constant term, positive 10. Let's do the exact same thing for our other 2 equations, right? So we're going to have some number multiplied by VA plus some number multiplied by VB plus some number multiplied by VC is equal to a constant. So the coefficient for VA in our second equation should be what? -1/8. What about the coefficient for VB? Exactly right. 1/8 plus 1/15 plus 1/20. So there are three terms that contain VB, so it should have three parts. And the coefficient for VC, -1/20. And the constant value, 0. And finally, we do it again for our last equation down here. So our coefficient for VA is 0. Savannah, what's my coefficient for VB? No idea? Okay, Jenny, how about you? Yeah, -1/20, right? So when I'm looking at this equation here, negative sign is divided by 20. So that's where that -1/20 came from. Let's see. Hannah, what is my coefficient for VC? +1/20. Oops, and that should not be 0 out here on the end. I made a dumb mistake there. What should the constant term be, Tyler? -5n. So we have three equations, three unknowns, and if you took my advice and bought a calculator that doesn't suck, you should be able to set up this system of equations and solve it. Yes, ma'am. What, a wire? That's, yep, exactly correct. 100% correct. Nope, do not apologize for that. You're thinking. That's what we're here to do. That's perfectly acceptable. All right, so if I solve this system of equations for VA, VB, VC, let's see what happens here. So I got 1/8, -1/8, 0, 10, -1/8, 1/8 plus 1/15 plus 1/20, -1/20, 0, 0, -1/20, +1/20, -5. Has anybody managed to solve this system yet? What did you get for VA? 155 volts. That is also what I got. Would a third person care to confirm his results? All right. What did you get for VB? 75 volts. All right. Same as I got. And then for VC, -25 volts. Okay. Also what I got. I solved the system. Nothing in particular. That's just, I use that sometimes, and then arrows sometimes is just, I'm getting to the next step. Sure, therefore. I solved this, I have this system of equations, therefore those are the answers. Works for me. Thank you, Drew. John. So are you asking, could you potentially solve this by using substitution? Sure. But it works out nicely and neatly in this one. Probably not most of the things that I want to do. So, absolutely, you're correct there, but in some instances, it's going to be a real pain in the butt to use substitution, and your calculators have system solvers. Well, hopefully your calculators have system solvers. If not, I would be willing to bet by this weekend you'll go out and buy one that does, because you're going to be using the heck out of it. That is correct. Well, so let me be clear about that. For your exams, I will not give you a problem that involves, let me not say involves, that requires you to solve a system that is larger than 3 equations, 3 unknowns. So what I mean by that is there might be, and we'll talk about that in just a second when we get to dependent sources, there might be a 4th equation involved that you can do a simple substitution in to make it 3 equations, 3 unknowns, that kind of thing. Or it might be something to where, and it would be hard to do for this, but for mesh analysis, if there are 2 resistors in parallel, you could combine them into a single resistance and wind up eliminating a mesh or something like that. So 3 equations, 3 unknowns is the maximum that I expect you to be able to solve, because it is the maximum that the calculator that the majority of you have can do. That being said, I think I talked about this on the very first day of class, the Casio 991 calculator. How much did it cost, Justin? 19 bucks at Walmart. Can solve 4 equations, 4 unknown systems. I'm not telling you that you need to go buy this calculator, because you absolutely don't have to have it, but that potentially eliminates one simplification or combination that you would otherwise have to do manually. Okay? So I'm telling you this, I don't own that calculator. Okay, so I'm not making money off of Casio in any way, shape, or form. I'm not getting kickbacks or anything like that. It is the most powerful calculator that is NCEES approved. So use it as a tool, because that's what it's there for. Yes. Yes. Not intentionally. So I might make some dumb mistake or something sometimes, and that'll happen, but for circuits, because everything is tied back to a physical principle and all that kind of stuff, it should not happen very often. Yeah, right. So in MathCAD, turn it down just a smidge so I can talk about this. So in MathCAD, you guys are going to be expected to solve systems of equations with like 4 or 5 unknowns, and you use a computer algebra tool to do it. I don't know how particularly that you guys were taught to use this in your engineering 120 series, but what I saw was that most students choose to put their guesses as 0. And sometimes you'll run into issues if you make everything, every guess value 0. So yeah, starting with 1 is usually helpful. And if you run into a situation where guessing everything with an initial condition of 1 doesn't work, change one of them to 0 and it should fix itself. All right, let's work another problem. I'm going to make this one. You want me to make it? Well, let's see. That last problem was maybe one small step below what I would put on an exam. Literally, it's not that. All right. I haven't made it. Actually, no. Yeah, those TI-30s. I feel sorry for but I've told multiple kids, like, I will buy you a better calculator if you cannot afford one. And they're like, no, I learned how to work everything on this. And it's like, all right, when we get to complex numbers, you're gonna come be begging me for 15 bucks. No, terrible. All right, so this is our circuit. 12, 5, 7, 3, 4. I'm going to make this a current source direction down. Let's make this 2IX, where IX is the current flowing to the left through the 12 ohm resistor. So our ultimate goal in this problem will be to figure out the power supplied by the dependent source. P dependent, comma, supplied is equal to question mark. So Cheston, this is going to go back to what you asked me about at the beginning of the class. I have a circuit in front of me. I have a quantity of interest. How do I get from having this circuit to the answer? Fairly reasonable question. They're usually multiple times. Okay. Now I would approach something like this. Obviously, because we are talking about nodal analysis, I'm going to wind up using nodal analysis here. Would be to define what I need to know in order to get that answer. So what quantities do I need to solve for that one that I'm looking for? And then how do I solve for those necessary quantities and kind of work my way down to what I have, right? So if I wanted to determine the power supplied by my dependent source, what do I need to know? I need to know the current flowing through my dependent source, and I need to know the voltage drop across my dependent source. Right? Well, the current flowing through my dependent source is twice Ix. So that part's at least kind of easy to figure out what's going on. The voltage will be a little bit more difficult, but that's where our nodal analysis comes in, because it tells us what voltages are effectively everywhere in the circuit. So what's my first step that I should take if I'm using my nodal analysis technique? Identify my nodes. All right. Here's node 1. Here is a second node. Oops, did not mean to erase that. There's a third node. Here's a fourth node. All right, step 1 has been taken care of. What is step 2? Set a reference. So which one do we want to be a reference? The bottom, okay. You guys are boring, but I'll deal with it. It is overwhelmingly connected to the most elements, so it's not a bad guess. It's actually the best guess, but it's less fun because there's less math to do. Sure. All right. What's step 3? Assign. All right. So I'm going to call this green guy node A. So it has a nodal voltage A. This red guy in the middle here, node B. So it has a nodal voltage B. VB, excuse me. And this blue guy over here on the right will be node C. So it has a nodal voltage VC. So because this problem has a dependent source it will have literally one extra step. And that step will be to express the controlling variable in terms of our nodal voltages. So before we write our KCL equations or anything like that, let's do that first, okay? How do I express that current IX flowing through my 12 ohm resistor in terms of my nodal voltages? So I heard VA minus VC over 12 and VC minus VA over 12. Which one is it? So it should be VC minus VA, right? Because the current is flowing from the right to the left. So it should be the right node minus the left node. So IX is equal to VC minus VA over 12 ohms. All right. Now we get to writing our Kirchhoff's current law equation. So the reason why I'm telling you guys to identify your controlling variables first is because that's probably the easiest thing to forget. You're going to be like, I have three equations, but 4 unknowns. Where the hell is my other equation supposed to come from? I've done KCL all over the place. It's that thing. So if you do it first, if you get in the habit of doing it first, you won't forget about it and freak out. Okay. All right. So KCL at node A. I like to do this. You guys don't have to. It's what I've been doing. I identify all the currents that I need to be paying attention to. So I'm going to have 2 currents that are directed down, 1 current directed to the right, and 1 current up. April, what is the current flowing down through the current source? Oh, I'm sorry. The current in green on the left-hand side flowing down to the current source. A little green arrow, the leftmost green arrow. Okay. Positive or negative? Negative, right. So current flowing down is negative 8 amps. Yes, I'm setting up all of these where the current is flowing out of the node, and that gives me VA will have a positive sign for my KCL at node A expression. VB will have a positive sign for my KCL at node B expression, and so forth. Who cares? I'm choosing these things and I'm applying KCL. That's all I'm doing. I could choose a different convention if I wanted to. I am using the one that gives me the least amount of negative signs all over the place because I make stupid mistakes when I have too many negative signs. Caitlin, I'm going to pick on you again, even though Ian's talking to you. Current flowing down through the 3 ohm resistor. Exactly correct. VA over 3. You've redeemed yourself. That's correct. And then I wrote it down poorly. VA over 3 ohms. Elijah, what's the current flowing to the right through the 5 ohm resistor? So why did you say VC? Yeah. So VA minus VB over 5 ohms. Let's see. Sarah, what is the current flowing up out of node A? So up and through the 12 ohm resistor. Pardon? So I disagree, right? So VA flows up through the 12 ohm resistor and winds up at VC. So it could be VA minus VC over 12. Which is negative IX, yes. VA minus VC over 12 ohms is equal to 0. All right, so we have our 4 terms corresponding to our 4 different little arrows that I've put up here. So let's move along to node B. So I have a current flowing to the left through the 5 ohm resistor, a current flowing down through a dependent current source, and a current flowing to the right through the 7 ohm resistor. Alan, I believe. What is the current flowing to the left through the 5 ohm resistor? VB minus VA over 5. Thank you. Absolutely correct. Savannah, am I allowed to pick on you yet, or do I need to move along? All right, Savannah, what's the current flowing down through the current source, the dependent current source? That's absolutely correct. That is, so typically speaking, I would write it as 2IX and then do the substitution as a separate step, but there's nothing stopping us from just going ahead and doing it now, since we've already identified that variable. Perfectly reasonable approach. So 2 times VC minus VA over 12 ohms. All right. So that's 2IX, and I've just substituted what IX is with in terms of my nodal voltages. All right. No, it's the current source. It's the current source because there's an arrow. Voltage sources will be the next thing that we cover in here. I am intentionally avoiding them right now because they actually kind of mess it up a little bit. So I will answer your question within 5 minutes roughly. Let's see, Drew, what is the current to the right through the 7 ohm resistor? VB minus VC over 7. Perfect, thank you. And I'll set that guy equal to 0 because we've taken into account all 4 currents leaving node B. Now we move to node C. And went slightly too far. I'm going to have this current directed to the left through the 7, current directed down through the 4, current directed to right through the independent current source, and a current directed up. So Brandon over there, because there's another Brandon over there. Brandon over there, what is the current flowing to the left through the 7 ohm resistor? Perfect. VC minus VB over 7. And then over here on the left-hand side, what is the current flowing down to the 4 ohm resistor? Absolutely right. You go by Daisy or Stephanie? Because in your Zoom thing it was Stephanie. What is the current flowing up through the 12 ohm resistor? Absolutely right. VC minus VA over square. I'm running out of people whose names I know. I apologize to the rest of you, so I'm just going to start pointing at people in a moment. Let's see. Jacob, what is the current flowing to the right? Negative 2 amps. All right. So we have 3 equations, 3 unknowns. So I'm hopeful that it is unnecessary for me to babysit you into setting up these equations this time with regards to how they get put into your calculator. So take a couple of moments here. And then when we figure out what VA, VB, and VC are, somebody tell me what's what. Anybody get anything yet? Elijah. That is not what I got, but there is always a possibility I typed. Pardon? I got 22.452. For VB, I got 22.968. And for VC, I got 15.019. All right. Have we finished solving the problem? No, because none of these are the power supplied by that damn dependent source. Right? So I'm going to scroll up here. Now that I know what all of those nodal voltages are in our circuit, how might I go about figuring out what that power supplied by the dependent source is? I'm gonna squeeze it in here and wind up writing an equation. All right. Current and voltage, right? So the power supplied P, I'm getting my subscripts backwards here. P dependent. Come on, pen thingy. There we go. Is going to be the voltage drop across my dependent source multiplied by the current flowing through my dependent source, right? But because I'm determining the supplied power, I have to pay attention to both the polarity of my voltage drop across my dependent source and the direction that the current is flowing, right? So if I want supplied power, do I want the current flowing into the negative polarity terminal or into the positive polarity terminal? The negative polarity terminal, okay? So I'm going to call this current I dependent, which means this is my voltage V dependent, so that my current I dependent is flowing into my voltage V dependent. So how can I express that voltage V dependent in terms of my nodal voltages? Negative VB. Is everybody okay with that? If not, I'm happy to explain it, okay? Because it probably bears repeating. Whenever I have a voltage defined with a plus and a minus sign, and I want to put it in terms of my nodal voltages, what I do is I say that the voltage at the positive, the nodal voltage at the positive polarity terminal, which in this case is ground or 0, minus the nodal voltage at the negative polarity terminal, which in this case is VB. So V dependent is negative VB in this case, right? So negative VB. And then my twice IX, Savannah already helped us out on that. So it's twice VC minus VA over 12 ohms. Oops, VC minus VA. And my calculator happens to store everything automatically, which means I can literally put in, you know, B or a negative B times 2 C minus A over 12, and it will spit out the answer. I get 28.450. All right, so let's circle back around to Keston's question of what the heck happens when we have voltage sources, because I have intentionally been avoiding them. All right, am I good to jump to another page so we can take a crack at another problem? Yes, sir. At least 3. Yeah. Oh, yeah. Yeah, 3. That's that's what I was about to say. Get into the habit of doing your homework in MathCAD because it'll take care of all the rounding errors for you. I understand that that can be tedious, but I understand also that it's wildly frustrating to have the correct answer in WebWorks say, nope, you're wrong. And it's because you're off by 1,000th or something dumb like that. So I definitely, if you're not going to do it in MathCAD, do as much as you can storing variables and all that kind of good stuff so that your rounding errors get minimized. But I definitely understand how wildly frustrating that is. Yeah, I love MathCAD with a passion. All right, let's stop talking about computer programs and start talking about circuits. All right, so let's work a problem here. This one's going to be a bit of a I don't know how difficult I'm going to make it as of yet. Actually, I have an idea. Yep. 12-volt source. I just got to make sure it has enough nodes that we can solve it with our calculator. All right, 1 node, 2 node, 3. All right, this is our circuit. This doesn't look like, I gotta give you resistor values actually. Let's do 9, 11, and 6. And let's call this current IX. Okay. So this guy has 2 voltage sources in it. We haven't done circuits with any voltage sources in it, so we're actually going to encounter both cases here, depending on where we put our reference node. So I'm going to go ahead and identify our nodes. Oops, I didn't need to do 2 of those. Yeah, that would have been bad. That was me not paying attention. All right. So we got another guy with 4 nodes. Which one do we want to be our reference? Who says bottom left? All right, so we got like 8 or 9. Who says top right? Like 3 people. All right, we're gonna do bottom. You know what? Screw those. Screw the majority. We're gonna do top right. Let's make this fun. All right. So with the top right node as my reference, we need to get into at least work a problem where we're not just arbitrarily using the bottom node, because I know for a fact that there are problems in your web work assignments where arbitrarily choosing the bottom node actually makes things harder. So choosing this top right node, I'm going to call this red node in the top left VA. I'm going to call this pink node at the bottom VB, and I'm going to call this bottom right node in purple or whatever VC. Okay. I have a controlling variable. What's my equation? So IX will be equal to what? Negative VB over 11 ohms. Oops. Because the current is flowing from ground, which is at 0, to node B. So it's 0 minus V, with the current flowing into the positive flow. All right. Yes. Generally speaking, yes. But there are some instances, and it has to do with the topic that I'm about to cover, where choosing one that's connected to less nodes, but connected to the most voltage sources will make things easier. All right, so let's start by writing KCL at node A. So I'm going to have this current direction down and this current direction right. Ian, what is the current flowing down through my voltage source? Anybody care to venture a guess? What does it mean to be an independent voltage source? The voltage is known and the current has current flowing through it has no relationship whatsoever to that voltage. So Kirchhoff's current law falls apart when we have a voltage source to deal with, okay? Or I say falls apart, we can't express it in terms of anything else. So what I'm gonna do, I'm arbitrarily just gonna call this current I VS down. So it represents the current flowing down through my voltage source. Okay? Because that's as good of anything that I can do with it for right now. We're about to get there. Yeah. What's the current flowing to the right? VA over 9. All right. Now let's move along to node B. Where I'm going to have this current directed up, this current directed up, and this current directed to the right. So I hope it's obvious, but I'm going to have just as much difficulty figuring out what the current flowing up through the voltage source is than as I did when I was trying to figure out what the current flowing down through the voltage source was. Okay? So I'm going to call this IVS up. What's the current flowing up through the 11 ohm resistor test? 11. Yep, VB over 11. And the current flowing to the right through the 6 ohm resistor, Andrew, I think Andrew Turner, is that your name? Okay, awesome, I didn't screw it up. Current flowing to the right. VB minus VC over 6 ohms. And normally we'd go ahead and write Kirchhoff's voltage law at node C as well, but I'm going to pump the brakes on that. Alexis, what's up? Not at all. So I've indicated the directions as down and up, but you've noticed something very, very important, okay? This current IBS, that is the current flowing down through the 12 volt source, is equal but opposite to the current flowing up through the 12 volt source. So what I'm going to do is I'm going to apply Kirchhoff's current law simultaneously at nodes A and B together, okay? So this is what I'm going to call a supernode. So I'm going to draw a circle around it to kind of help you guys see what it is I'm talking about, because I heard a lot of oh my goshes and stuff like that. So you're like, oh Jesus, jackass is making us do something even fancier. Okay, so I drew some dots around this supernode. And if I apply Kirchhoff's current law at this supernode simultaneously, what I'm doing is I'm literally just adding up the equation for KCL at node A and KCL at node B together. Because I can say that 0 plus 0 equals 0 all damn day, right? And what happens is that our current source, or excuse me, our current flowing through our voltage source cancels each other out. It's thrown away. It's not even remotely necessary anymore, right? So instead of this, I get KCL at supernode A, B is just VA over 9 ohms plus VB over 11 ohms plus VB minus VC over 6 ohms is equal to 0. I have a supernode everywhere I have a voltage source, okay? Because I have to avoid setting that weird thing up. So I'm going to have a second supernode that's involving that dependent source, which is why I didn't bother writing an equation for it. Okay. So I'm going to circle that guy as well. I just forgot something that I need to do, so we'll circle back around to that in a second. All right, so here's a problem that we have just introduced that I just remembered. We have a single equation relating two nodes. We need to get two equations for those two nodes. Anybody have any idea where that second equation might come from? Exactly right. So anytime that we have a voltage source, we are going to need to write a voltage relationship for that voltage source in terms of our nodal voltages. So in this case, we have the voltage present at the positive polarity terminal, VA, minus the nodal voltage at the negative polarity terminal, VB, is equal to the voltage supplied by the source, 12 volts. So our voltage relationship equation for supernode A, B is simply VA minus VB is equal to 12 volts. Sure. What nodal voltage is connected to the positive polarity terminal of the 12 volt source? VA minus the nodal voltage at the negative polarity terminal, which is VB. So that's why VA minus VB is equal to 12. And we're going to do it again with our other dependent source here, right? So let me talk about that real quick. We are not going to write a Kirchhoff's current law equation for node C at all. The reason that we are not going to write a Kirchhoff's current law equation for node C is because node C is connected through a supernode to our reference. And we never, ever, ever write KCL equations involving our reference node. Right. Well, it's pointless. We know it's all zero in the wash. It's really no point to doing it whatsoever. Okay. So anytime that we have a supernode that contains our reference node, we do not have to write a Kirchhoff's current law equation there. We only have a voltage relationship. So in this case, that voltage relationship should be negative VC is equal to 3IX, because the positive polarity terminal is at our ground. The negative polarity terminal is at VC, so we have 0 minus VC is equal to what the voltage source tells us its value is, which is 3IX. So we, voltage relationship for supernode C, comma, ground is simply negative VC is equal to 3IX. And we know that IX is negative VB over 11 ohms. We're done. 3 equations, 3 unknowns. We can throw it into our solver and figure out everything about this particular problem. The voltage relationship equation. I can't write a Kirchhoff's current law equation, but I can do a voltage relationship equation, and not I can, I have to do a voltage relationship equation for every voltage source in my circuit. because I don't do KCL including my ground mode. So the current leaving my ground, and never do KCL with the current leaving my ground, because it's redundant information. It's all carried in my other equations. Pardon? All right. So at this point, solving things should kind of be old hat. I would like for you guys to work on the in-class assignment for the remainder of our class meeting, which is a whopping 35 minutes. I am hopeful that you'll be able to solve all three, but I am also doubtful.